so that's meters.
Oh, okay.
All right, other questions before we tackle the, potentially the more complex of the two? All right, so I've got my circle there, or my wire. Again, this is a wire. Got it. So something strange was happening in the other room with this, with the smart board. It's the fact that occasionally it would just change colors. I'm not quite sure if that's a glitch or some setting I have. All right, anyway.
That's a pretty solid circle.
You know what? That is a pretty solid circle.
Stay. All right. So now we're going to figure out what is the magnetic field at this point right here. Again, I'm going to create my Gaussian circle, or Amperian loop, whatever you want to call it. That's supposed to be a circle. A radius little r. And big R is the radius of the wire, which we know from over there is 0.07 meters. And I recognize that there's a mistake written over here. That should be a 7 and not a 1.
Oh, that's peculiar.
It's the new math.
Yeah.
7 equals 1.
God.
All right. If the current density is constant, first off, therefore, if I find the current density at some part, I find the current density at all parts, if it's uniform. So current density is current divided by area. Well, I know the current for the entire circle, or for the entire cross-section of the wire. I can figure out the area. So my current for the entire wire is 5 amperes over 2 pi 0.07. And that's not the formula for area.
Close.
Pi 0.07 meters squared. And so you end up with, figure out what the current density is. Which is some magical number that will make your lives just a little bit better, I assume.
324.81 amp over meter squared.
Yep,
I got the same thing.
okay. But what I really care about is how much current is inside my Amperian loop. How much current is flowing through this part? Well, I know what the current density is, so that's got to be equal to the current that's flowing inside my loop there over the area of that loop, which is pi times, oh, I guess never specified r, did I? Let's make little r brighter than that. Little r equals 0.03.
I guess too.
Well, given that 7 equals 1, it's possible 3 equals 2 also. So
Okay. Yeah, I'll go
times
with that.
0.03 squared. And so from this, we can figure out the amount of current that's inside my virtual loop.
Got 0.92 amps.
Anyone else? Good confirmation?
Point 92 amps.
Yeah, that's what I'm being told. Was I lied to?
I don't. What are we using for current? Are we using 5 amps again?
No, 5 amps is for the entire wire. I'm figuring out how much is just flowing through this part.
Oh, okay.
So this was my,
That's
Yeah,
okay,
that's
yeah,
equal to
yeah,
this.
Yeah, yeah.
I got the same thing.
All right.
192.
so we seem to have
Yeah.
a groundswell. So now it's very similar to what we just did. I here is 0.92. Multiply that times u, and you've got the line integral. And then divide by 2 pi r, where r is 0.03, to get the magnetic field.
Ah.
Do you want the line integral or do you want the
the magnetic field.
But the question asks for both.
So the line integral is 1.15 times 10 to the negative 6 Tesla meters.
One more time?
1.15 times 10 to the negative 6 Tesla meters.
You're carrying. Does your back hurt?
Mine does.
And so the magnetic field would be this divided by, that divided by. Two pi. 0.03.
Okay, so 6.12 times 10 to the negative 6 Teslas.
Now, just a quick and dirty check. Oh, actually. Yep, never mind. I was gonna compare this to what we had before, but it's not a simple comparison.
Okay, how do we get from the integral is equal to 1.15 times 10 to the negative 6 down to the magnitude of b is equal to that?
All right, so the integral of b dot ds, first off, it's a dot product. So it cares about saying how much is parallel to the other. ds, I'm doing a line integral starting at some spot here and I'm working my way around. My magnetic field is in the same direction. No matter where I am, my ds and my b are in the same direction. So from the dot product point of view, it's the integral of just bds.
Okay.
Because the angle between them is 0 no matter where you are. B is a constant. Because of symmetry, this B is the magnetic field strength. There's no reason for it to be different in one spot or another. So now I'm doing an integral along this path here. It's a closed path, that's the circle in the integral, that's what that's telling us, is that we will end up back where we started. So I'm doing an integral along the line, basically it's finding the length of this circle, which is 2 pi r.
Oh,
Right.
okay, oh. Oh, okay, that makes more sense. Thank
Okay.
you.
So that's gonna apply for most of us.
It was the same thing that he did at the, like on the whiteboard at the bottom right, but just, he like wrote out the steps there, like the solving for B steps. Yeah.
That's a fair assessment.
That makes sense.
All right.
Thank you.
Other questions? Oh. Jacob says hi to everyone.
Hey,
Jacob.
They said hi back. I don't know how well you can hear.
I said that a while ago.
We eventually responded.
Yeah, I'm living in the past, so just give me some time.
Oh wait, Dr. Fox had a question about master set. Well, this master set question 2b. So because the line is moving diagonally, like if I remember.
Sorry, which one are you talking about? Which one?
2b, where like the origin of the wires
Sure.
is 0, 5, 0.
Yeah, okay.
And then it goes towards, and then it ends at 10, 0, 0, which is where the
wire's just going,
field is.
okay.
Like, can you use the same formula as an A, but you have to change like the bounds? Or is it a lot more than that?
If you're doing A from scratch, so you're starting with the Via-Savart law and doing it that way, then the only difference between A and B are
Is it the
the
bound?
limits of integration.
Oh, okay.
If you are using the formula to do part A, that basically Ampere's law, then you're going to be doing an integral. That's for B, I said calculus. you're gonna integrate and you'll have limits of your integration.
Okay, because I integrated for both A and B. And C.
Okay,
So
then-
that's fine?
Yeah,
Okay, so it just depends on which method you follow? to
Right.
Solve it? Okay.
right. So if you did calculus for part A, then part B is just change the limits of integration.
Okay.
You've done the hard work already for B.
I had a slight question for one, so like,
And the answer for B should be less than the answer for A, because it's a
Okay.
smaller wire. So you got a question for what?
are we assuming that's in, that's out?
The dot's coming this way,
Wait, out, in,
yeah.
okay. Then is there technically any current flow if they're the same signs?
The current's flowing towards us, so that's 4 wires with the current flowing either towards us or away from us.
Okay. But there is current flow.
Yes, there is current flow.
Okay, that was my question.
Yeah, it's not flowing along the dotted lines, it's flowing.
In or out?
In or out.
Okay.
Apparently, your other question was so controversial. You had to
Just had to
leave.
go.
When you're calculating, for that question, when you're calculating the direction of the magnetic field, I mean, if you have current going down, but depending on which way you twist your hand, you can have, I mean, you could have the clockwise motion going in the negative K hat or the positive K hat. Or are you supposed to
No.
use the V cross V? Actually, there's no external, so.
If I have a current that's flowing out, right hand rule, my magnetic field's gonna be flowing around like that, so my magnetic field is this way. It doesn't matter, if I'm doing my right hand rule, it's gonna be the same no matter what.
Yeah, okay, so you're not, whenever you're asking for the magnetic field, do we need to put, like a unit vector after it, like an I hat, J hat, or K hat, for this specific question, because,
You're talking about number 1?
no, for number 2.
Oh, sorry, number 2, you will need to establish a direction there. Yeah, because I didn't ask for magnetic field strength, I asked for magnetic field, so
Yep.
you do need a direction. And if you stick with I hat in the X direction, J hat in the positive Y direction, and K hat in the positive Z direction, that probably will lead to less confusion.
I forget, for rotate, I remember we went over this, in 251 for rotational motion.
Right.
But if you're using a right-hand rule for rotational motion, is it IJ and then K goes first U, and that's, so K hat would be like a,
I hat cross J hat is K hat. Sorry, did I miss your question?
yeah, I guess if I'm looking at something and it's clockwise, would I just put that as K hat? Because it's going,
Right hand. So if I have something that's rotating clockwise, then my fingers would curl in that direction and the vector would be away from us.
okay,
So that'd be negative K hat?
Depending on how you set up the system, but quite possibly.
okay.
Under the brainwashed math system, yes, that'd be negative K hat.
Can you technically use the Hall effect to solve question 1?
No.
Oh. So you have to do like each individual point?
Yeah, each individual one, you do a right-hand rule for each individual one and
Okay.
see, at some point, because you're asked to find in the center, I believe?
Yeah.
Yeah. So you do the right-hand rule, and in some cases, you'll get, a magnetic field going this way and one going that way, well, those will cancel out.
So the ones that'll be the strongest is the one that with the most fields pointing towards the center?
None of the fields will point towards the center. They're either, because remember, the magnetic field is, using the right-hand rule, And if I've got, just take 3 of them here. This one at the center is a magnetic field going that way. So we call that A, B, and C. This would be B sub A. This one, magnetic field's coming out, that's gonna be going that way, this would be B sub D. And then C, at the center, going that way, that'd be B sub C.
Also, you do center to the point when you're finding out the direction.
When you said center of the wire
Mm-hmm.
to the point in question, yes.
Okay.
So if it is flowing in the other direction, the magnitude would just be negative?
Technically, the magnitude's the same, the direction would be the negative.
It's just the direction,
Yeah, the direction switches.
but that doesn't affect the magnitude of
It should, because the magnitude is mainly dependent upon how far away it is, if you're outside the wire.
Do we have a lab today?
No, we're not gonna do a lab today.
Oh.
Shoot.
Dang.
I see this as a win personally.
I'm gonna do a demonstration of the lab that you would do, and then talk about why it might be considered a win for you. Even though it is my favorite lab,
Let's do it.
it's a pain.
Why is it a pain?
Oh, well,
When I do the demonstration, I will point out, or perhaps you will notice why it's a pain.
This is a physics lab.
Yes,
They're
that's
designed to fail.
Yeah.
A is a physics.
Not every physics lab is a pain.
designed for physical pain.
Only if you touch the wires wrong.
Hey, there's a guy, I saw this guy on Instagram that breaks all the laws of physics, that's all I'm saying. He can do those Russian push-ups, where you can just float in the air,
No,
that's crazy.
dude.
No, yeah,
No, he can't.
yes, he can.
No, he cannot, dude.
Alright, well, I assume that at some point he will share a link.
I have a physics question. Okay, so yesterday I was charging my phone, right? And I'm trying to figure out like how to describe it. Okay, so you know how like iPhones make a sound whenever you plug it in and it indicates that it's charging?
Okay, I'll trust you on that.
Yeah, so that's what happens, right? When it's connected to like a power source to charge it, right?
Okay.
And I used a cord yesterday that I had like just unplugged and it wasn't connected to the wall, but it still made that sound and popped up like it was charging for like a brief second. Why would that happen?
Capacitor. Or when you play, because I noticed that on,
It was almost like there was something stored like a super small amount of like something stored or like something that was still charged.
I would hope it would not respond to that little amount if there's anything there.
I just
Because
don't
if-
know why it would do that.
I noticed that if I've got, when I plug stuff into an iPad,
Mm.
that it will come up with basically this thing saying how much battery power you have left.
Mm.
Whether it's charging or not, it comes up with this thing that make me think, oh, it's charging, but it's really not charging. So I'm wondering if there's something when you plug into the slot.
Just has like an indicator that detects a charger and then like it thinks it's charging for
Yeah,
a
could it
brief
be like a
second,
physical
but then it's
thing?
just like, no.
I was wondering if, I was picturing a physical thing, but.
Yeah, like there's some sort of sensor that would be like, okay, there's a charger here, make the sound, make sure that it's charging.
That's
Yeah.
my thinking right now, but if you have otherwise, let me know.
To add to that, I have a block, that same thing, but it has a light indicator, and you unplug it, and while it's unplugged, it can be with the light on for 10 minutes. But if you go and you put a phone up to it, instantly like it's drained.
Huh.
So when she asked that, I was like, well, maybe there's something to it, cause I can bring it in when it's a big computer block, it's like an anchor block, and it just has a blue indicator to tell you that it's on, and it'll stay, if you unplug it, it'll stay on for a while.
unless you put it, something near it.
Unless you plug it into something. And then the instant it plugs in, the indicator shows up, and then it'll turn off instantly.
It almost sounds like they messed up in the design or it wasn't worth their effort to fix that.
I have a physics question, can I draw it on the board?
Sure. While he's doing that, there was the question that came up a couple weeks ago, yesterday, at some point, about the inner core of the Earth flipping directions.
Yeah, sorry.
It actually is, it depends on your point of view. It is now traveling slower than the Earth is. So from our point of view, it's going backwards, but it's still from sort of the sun's point of view, still spinning in the same direction as it was before, just slower than the surface of the Earth is. So why it's doing that?
Does it affect us in any way?
Say it again?
Does it affect us in any way?
Not the inner core, to my knowledge. It's when the plasma changes directions, that's gonna affect us.
Our days are technically shorter because of it, but like,
Isn't that
2
like
seconds.
your wife's shebang? She does stuff like that, right?
She did geology.
Like Earth stuff?
Yeah.
I remember. What, she would be the one to know, yeah?
Yeah, she doesn't know that.
Okay. So there's a table here.
Right.
Two objects on it, there's a pulley here with another mass hanging down. Obviously it's gonna go down due to gravity, and it's gonna pull this box.
Okay.
But there's friction between the two boxes, but there's no friction with this box, the bottom box and the table.
Okay.
So wouldn't this all just move as a unit?
Alright, so we have, not necessarily, if the hanging mass is sufficient enough that it would jerk the top block, that top block would suddenly, we're now dealing with kinetic friction, if the top block slides on the block right below it. There is you can calculate the maximum hanging mass so that it doesn't do that, so that they would slide as a unit.
But I'm not understanding what would hold this mass that way. If
Nothing with that mass is still gonna move this way. It's the question you would ask me was, do they move as a unit? They will both move. But